So we're going to look at polygons. Chapter 6 has to do with, we're leaving triangles, sort of. We'll still continue to talk a little bit about triangles, but we're going to focus on mostly quadrilaterals. Okay. So first of all, let's define what a polygon is. You tell me. I bet you already know what a polygon is. Okay, it's a shape. Okay, good. We got a shape, but we got to let's close all the Chromebooks. Chromebooks got to be closed. Yes.
All straight edges.
Okay, some things we need to know. So polygons are shapes composed of straight segments, right, of line segments, which implies that they're straight. And the segments make up the sides of the polygon, but they have to be straight. They can't be curved, right? So we got straight sides. All right, let's maybe make a list of what we need here. So we need to have straight sides, and let's say I've got a polygon with 4 or 5 sides, let's say. Okay, does this constitute a polygon with 5 sides? Let's say I've got, let's start with a really simple one. We'll start with one with 4 sides. Okay, is that a polygon?
Yes.
It is, right? It is a polygon. What if I want to look at the anatomy of a polygon? We'll just use this one. What do I call these things right here?
Vertices.
Yeah, right. One of those is a vertex. All of them combined are vertices, just like we had with triangles, right? So that or angles even. So that's no big deal. What do I call these guys right here?
Sides.
Good. Okay, very good. So let's say I want to draw a polygon that's got 5 vertices and 5 sides. The number of vertices would always have to match the number of sides, wouldn't it? Right? Okay, so does this work? Is that a 5-sided polygon?
Depends on the angle of the middle point.
Okay, so let's assume it is what it looks like. So that's a straight angle.
Okay, then
Okay, so that's right. So that's not a vertex, is it? Right. Okay. It looks like it could be a midpoint, but it's certainly a point on the scale, right? Okay. Okay, so one thing we can say about a polygon then is that it's formed by, what's the minimum number of sides a polygon could have? 3. Yeah, it couldn't have 2, could it? 2 wouldn't work. If I did, what would a 2-sided polygon look like? Well, it'd try to look like that, but that's not a polygon, right? A polygon has to be able to enclose some area, and that doesn't, right? So it's formed by 3 or more sides, and those sides are segments, right? So they have to be straight. And we just showed that no 2 of the sides can form a straight angle, right? Another way of saying that would be, so no 2, oops, so no 2 adjacent sides meaning they share an endpoint or they share a vertex. Does that make sense? So no 2 adjacent sides could be collinear, because if they were, they'd form a straight angle, right? Does that make sense? Okay, so let me try another one on you. So how's this? Is that a polygon? Yeah, why don't you close those Chromebooks, please, all the way close. So yeah, that fits all the criteria, doesn't it? Right? It's got how many sides? 1, 2, 3, 4, 5 sides. None of the sides, adjacent sides, are collinear, so no straight angles. That works. It's a little odd looking, but it works. How about this one? What do you think? Jill's shaking her head no.
That's two separate polygons.
Okay, yeah, that one looks a little funny, and I haven't told you why that doesn't work, but does somebody want to suggest maybe that's not? Something went wrong there. Somebody want to suggest maybe why that's not a polygon? Okay, the lines are crossing each other. What's a mathematical way of saying that? Because I could maybe tilt this top one so it doesn't look like lines are crossing, right? Like I could make it look like this instead. I could make it look like. So yeah, that's not what I want to do. So make it look like. Like that instead, right? That still wouldn't be a polygon. What do you think? Anybody got a way of saying, what do you think, Emma? How could I, so what's wrong? This seems to be, this is the danger zone right there, isn't it? That's the weird part of that polygon. How could I set up some rules to follow that wouldn't allow, what do you think?
Didn't you say that it had to have like the same number of vertices and sides?
Oh, okay, it would have to have, that's not a hard and fast rule, but we're gonna see that that's true. That ends up being true. But what could you, look at the examples of, here's a polygon that worked. This polygon worked in most places, but not at that vertex. What's different about that vertex than all of the other vertices that work okay? What do you think?
Intersecting lines.
Well, okay, but those lines don't intersect, right?
It's shared between two polygons.
Say it again.
It's shared.
I mean, okay, so yeah, you could say it's shared, but even then, we want to get more mathematical if we could.
Well, isn't it because it has to be enclosed and it's two different enclosed sheets?
I mean, you could make all those arguments, but there's a simpler way, simpler rule we can apply that would summarize all of those. Look at all these vertices that work compared to the one that doesn't work. What do you think?
Because there's one vertice for two like parts where lines meet.
Okay, so one vertex where two segments meet was okay, wasn't it? Right? That works. If two sides meet at a single vertex, that works. So therefore, if we look at this from the perspective of a vertex, for it to be a legitimate vertex in a legitimate polynomial, or excuse me, polygon, for it to be a legitimate vertex, how many sides could meet at a vertex? Two only, right? A vertex has to be a place where only two sides meet. What's wrong with this one? There's four. Yeah, it doesn't work, right? Can only be two. So there's our other criterion, and just those two criteria rule out all the possible permutations of polygons that fail, right? Of wannabe polygons that fail. Okay, so two, we end up with, how do they say this in the book? They say each vertex or each side intersects exactly two other sides, one at each endpoint, which is fine. We can say it that way. So that's the language that our book is going to use, right? But what we said, I think, is actually maybe a better way of saying it. It says the same thing, I think, more concisely. We could trade this if we wanted to for the statement. Vertices, or each each vertex connects exactly two sides. I think that's a simpler, better way of saying it, but our book says the top way. Mean the same thing though, right? Okay, so is how about this then? Is this a wrong with that one? Okay, yeah, one side's not straight. Those are pretty, I mean, you're gonna see some examples of those. Those are pretty simple. Okay, what about these? You notice something different about these two polygons. That one versus this one. I could have drawn an infinite number of them in the left column and an infinite number in the right column, but there's something that's kind of different about those. More sides are okay. More sides look even. I'll draw another one because that's really not a big enough sample size.
One's symmetrical and one's not. You can split in half and make it symmetrical.
Okay, that's true. So there's a bunch of things that are different. Let's see if we can find.
That one goes in and the other one's down.
Oh wait.
So it's like a little.
It's pretty bad stock. You know,
Those ones,
what are you noticing?
those ones did in.
Ah, yeah. Okay. Notice that you've got, and we talked about exterior angles in the last, about exterior angles with triangles, didn't we? Triangles are just polygons. Polygons with three sides, right? So if we talk about a triangle, there's a triangle. If I extend one of the sides, then I form, I form an exterior angle, right? If you look at all of the exterior angles on these polygons right here compared to these, what do you notice? Yeah, these are all greater than 180, aren't they? Right? Look at all these exterior angles. Those are big angles, bigger than straight angles, right? What do you notice about at least one of the exterior angles on these? Yeah, they're less than 180, okay? And what that causes is it causes what's called concavity, right? These are, if we want to label these things, we would say these are concave polygons, and these are convex. Have you talked about this before?
No, but I did the assignment.
Oh, but you did the assignment, so you might have already done the, it's a pretty simple assignment.
Calm down.
Okay, concave, convex, those are words we'll use a lot in a little bit in math, a lot in science, like in my physics class when we talk about optics later. We'll talk about convex and concave lenses. What do you suppose a convex lens looks like if you look sideways at it? It's going to look like that, right? If you look at it on its edge, it looks like that. Concave would look like, if you turn it sideways, like there's the lens, you turn it sideways, it would look like that. Thicker on the edges, thinner in the middle, right? Okay, so concave, they have like caves in them, they've been caved in. But once again, we need a mathematical way of expressing this. In math, we don't like to use language like dented in, or no, that's just not mathematical. It's too flowery. We need very precise, unambiguous mathematical descriptions. How could we differentiate this group from this group mathematically? Kirk, what do you think? Say it again.
Irregular.
Sure, but we could have irregular polygons on both sides, couldn't we? Yeah. Right? Okay. Okay, that's not a bad way. That's not a bad way. There's even a, because sometimes it might even be hard to tell, or it might, but there's even an easier way. What do you suggest?
If you extend each line segment into a line, if the line intersects another side of the polygon, then it's concave.
Very good. Okay, look what we can do. if we extend any of the sides and turn them into lines, right? Another way of saying that is any line that contains a side of the polygon in this group over here, those lines they have no possibility of ever passing through an interior part of the polygon. Does that make sense? If I extend these outward, they go forever, but they'll never pass through the inside. Now over here, that's not the case. We find at least one side, actually it'd have to be at least two sides, on each of these, and this, a whole bunch of them on this star, right? But on this one, I've got two in particular. If I extend this side like so, it's got a whole bunch of points on the line, infinite number, that intersect the interior of the polygon. They pass through the interior of the polygon, right? So if you can do that, if a line containing a side of the polygon passes through, any line containing a side of the polygon passes through the interior, then by definition it's concave, right? That's our mathematical way of saying like dented in or caved in or something like that, right? Okay. Last issue, and this is really a pretty lightweight section. It's pretty introductory. What do you notice about this? Is my drawing skills are really gonna, or my lack of drawing skills is gonna be evident here.
Better than mine.
Okay, I didn't draw it very well, but what do those congruence marks mean? Okay, all the sides are congruent, which means that their lengths are equal. So what would we call it? Equilateral, right? Just like a triangle. Okay, how about this one? No. Okay, what's that telling you? It's equiangular. Yeah, equiangular.
Wait, so what makes a parallelogram
Parallelogram, we'll get there. That's next section we're going to talk about parallelogram.
Doesn't that one have two parallel sides and two parallel sides and two parallel sides?
No, because you didn't say that they were parallel, so you should assume things, Joe. I will assume things.
But we know that they would be parallel since all the angles are equal.
Wait for someone to say that all day.
You got me there, Elton. Just too smart.
It's not perfect for regular.
Okay, what about that one?
It's a regular.
Equilateral.
Okay, it's both. Anybody know what we call a shape, a polygon, that is both equilateral and equiangular?
Regular.
Perfect.
Perfect.
Perfect. Good guess.
No, it's not like
I hope
that.
It's called
Regular.
Lateral?
regular.
Oh.
So a regular polynomial is both. Okay. Okay, I'm going to show you a trick that doesn't come up in the book. Maybe it does later, but it doesn't come up now.
I'll laugh.
Okay, if we want to, you're going to come up with an important formula here. What if we want to add up the sums of all the interior angles in a polygon? We did that for a triangle and it was how big?
180.
180. Okay.
360.
Any suggestions about what this might be? What do you think?
360 plus 180, which is
So 540? Okay. That's your how'd you get that?
I connected one of the points to another, and I got a triangle.
Okay.
And I related triangles are 180.
So if we split this up, okay.
That's not a square though.
You're right.
So,
It's good enough.
Okay, but how about if we do this?
Wait, so is it 180 times 3?
Okay, what is it? Say it again.
I didn't say
Who
it.
said that?
180 times 3, but I don't know.
That's right. Okay, it's 180 times 3. How come?
Because it's 3 times.
Because, okay, and we can always do this, can't we? If we connect the vertices, like let's say we just take one vertex, that's going to be our hub. And we don't really have to even do it that way, but we connect all the other vertices. We can always subdivide any polygon up into a whole bunch of triangles. They don't have to be the same, but just a bunch of triangles. We know that the sum of the interior angles in any triangle is always 180. And so if I've got 1, 2, 3 triangles, then that must be 3 times 180, which is 540, right? Okay, now let's see if we can establish a pattern here. How many sides are there in this polygon? 5. Okay, so this one had 5. Let's try another one. What if we take, okay, that has 4, right?
Yes.
How many triangles do we get? Okay,
For every
let's do
side
another
you add,
one.
you get
I
another
want you to see a
triangle.
pattern.
For every side you add, you get another triangle.
Oh, I'm trying to watch.
Okay,
2 less than how many sides are
what do you get?
2 less, there's 2 less.
2 less than how many sides? So this is 1, 2, 3, 4, and it's a 6-sided, right? Everybody see that? I'll do just one more to illustrate it even more, so it's gonna be hard to draw, but.
So that's 2 sides.
Okay, so now we go there, 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 and there. Okay, so it's 8-sided. We got 1, 2, 3, 4,
You made
5,
the guess.
6 sides. Okay, did everybody buy what Kirk's saying? So if we take an n, now let's be really general with this. We took polygons of sides 5, 4, 6, and 8. So you make a prediction then. What if we have an n-sided polygon? Okay, why would I say an n-sided polygon? Okay, but say it again. Okay, that's true. They all meet, and that might help us see what Kirk saw. But why would I want to express this in terms of an n-sided polygon?
So it's always gonna be n minus 2.
Okay, because what's good about n compared to like 8 or 10?
Well, it's a variable.
It's a variable. Yeah, it's unknown, isn't it? Right? Okay, this is something. This is a big idea. I know this might seem kind of simple, but this is something we do in math all the time. Whenever in math we want to come up, or physics, we want to come up with some kind of a relationship that is as general as possible. Because if it's totally general, we can use it again, right? We can use it in all kinds of situations, right? So we'd rather not come up with a specific answer. We'd rather come up with some kind of a general relationship that we could apply to any possible polygon in this case, right? So if we can come up with a relationship in terms of n, well then, once we get that relationship, we could just say, well, what if n is 13? What if it's 100? You know, and we get an answer immediately without having to reinvent the wheel every time, right? So for an n-sided polygon, which we would just call an n-gon, how many triangles would that contain?
N minus 2.
So if it contains n minus 2 triangles, then the sum of the measures of the interior angles of an n-gon would have to be what?
N minus 2.
N to the n plus 2.
Yeah, n minus 2 times 180, because that's how many triangles we're adding up, right?
Or n times.
Okay, does that make sense? Okay, so let's say that again. So the So there's the formula we would use. Now think why, because you guys told me you saw this relationship here that the number of sides minus 2 predicts, maybe let's put that away. The number of sides minus 2 predicts the number of triangles contained in that polygon, right? Each polygon encompasses exactly 180 degrees of area, right? So then wouldn't we have a total area of the number of triangles times 180 degrees?
Yeah.
Right?
Oh.
Okay, it makes sense? So what would be, how much, what's the sum of all the interior angles in, well, I don't even know what this is called. What is it dodecagon, 12 gon. 12-sided polygon.
1,800.
What does it give me? 1,800. 12 minus 2 is 10 times 180 is 1,800, right? See how that works?
Yeah.
Okay, good. All right. How much time we got?
14 minutes.
Oh boy, I used to almost all the time, didn't I?
Better not do anything
I just
today.
went to the trivia.
Let's talk about
Trivia.
something for 14 minutes.
For 14 minutes?
Parallel
Okay.
universe is real. Oh my god. Can we not start with this?
Don't
That's
go
gonna
as
take more than
when you go
14
through them.
That's gonna take way more than 14 minutes.
When did they find those?
Once you get, I would like to answer some questions. So once you get a Chromebook, work for a few minutes, and I want to have a chance to answer. People have questions about either of the tests. Now's the time. Yeah. Yep.
Okay.
I still have like half that
If you don't
performance
have
test.
Oh yeah, we'll take care of that.
Can I just work on the other test?
Yep,
I only
yeah,
have,
yeah.
Like 2 problems.
Yep. Yep, absolutely. Yep.
One was 6.2.